to Poland for this talk.
Well done. I was going to point out to people here that you're someone who's normally just up the road in Philadelphia, but now in Poland is where Lawrence is coming to us from.
Yes. So I assume you can see my screen and you'll yell at me if something is wrong. Otherwise, I'll just keep going.
Okay, well, I'll actually just formally introduce you. So this is Lawrence Dunn talking to us from Poland and talking to us about syntax monads. Go ahead, Lawrence.
Okay, yes, syntax monads for the working formal metatheorist, I might add. This is the more category-theoretic side of my dissertation at the University of Pennsylvania with my advisors Val Tannen and Steve Zdanswick. And let me give you an idea of what kind of problem we're working on. We are computer scientists, not professional category theorists, if there is such a thing. And we have been seeking an abstraction of abstract syntax trees so that we can reason about syntax generically. And what I mean by that is I want to reason about things like capture avoiding substitution, and I want to do this inside a proof assistant, but I want to do this in a way that is not specific to the syntax of any one formal system like the lambda calculus. This sort of reasoning is actually a huge bottleneck in formally verified programming languages and things like that. So I want to just do this once and reuse that effort over and over again. A lot of people have thought about this sort of problem, and one of the basic observations in this space is that depending on how you define syntax, you usually get some kind of monad, often a free monad on the category of sets. And this seems like a very promising start because monads seem to say something about substitution, but this idea by itself is not so useful because this is not the right kind of substitution. This is like a very plain kind of substitution, but not the sort of capture avoiding, renaming bound variables substitution that comes up in programming languages all the time. There has been a lot of prior work on extending the notion of a monad to be more useful in this space, but typically prior work thinks about syntax in a way that I don't. It thinks about syntax as something that's inherently well scoped. So you don't have just a notion of term. You talk about, I have a term in a given typing context. And in my experience formalizing things, that's just not how I've thought about it. And so the abstraction that we've ended up with is a little bit different, maybe more primitive, I'm not sure, but it seems to get the job done. So in this talk, I'm going to introduce something that we've been calling a decorated traversable monad, or a DTM, and this is our abstraction of syntax. DTMs are, in particular, monads on the category of sets. So they're very simple. And it's the functor itself that has this extra structure that we call decorated traversable. And it's the extra structure on the functor that's going to give me the expressiveness that I need to do what I want to do. Now, DTMs, you'll be pleased to know, can be defined as monoids in the category of decorated traversable functors. And that's a nice characterization. But even nicer, for my purposes, is that we can give a Kleisli style characterization. I'm using that a bit loosely and informally. But what I mean is that we can define DTMs in terms of a single combinator that is rather expressive and subject to just a small number of axioms, much like a Kleisli triple for a monad. And it's this Kleisli style characterization that is useful for practical things. And speaking of which, there is a large applied side of this work. We have a Coq library called Tealeaves that I just presented a few hours ago right here in Białystok. And Tealeaves is a Coq library where we do what I said, we formalize generic syntax infrastructure, but it's totally generic over an arbitrary DTM. So if you have some kind of formal system, it's some kind of syntax. If you can prove that that syntax is a DTM, then you can use Tealeaves and reuse all of this work we have formalized. So because this is applied category theory, let me say a little bit more about the kind of applications we have in mind. We care a lot about formal meta theory. So what that means is our workflow looks kind of like this. If this means anything to you, we are doing deep embeddings of formal systems into type theory and then reasoning about them to prove their correctness. So the workflow is you fire up the Coq proof assistant and you start by defining the syntax of some system that you care about, like a lambda calculus or some kind of type theory. And then you give some rules for manipulating that syntax, right? These could be inference rules, typing rules, whatever, and give some kind of semantics to that syntax and then prove something about the relationship between syntax and semantics. Of course, we're doing this in a proof assistant, Coq, and that gives us a lot of confidence in our reasoning because when it comes to this kind of stuff, the devil is very much in the details. And Coq is going to hold our feet to the fire, make sure we dot our I's and cross our T's and do everything very precisely and explicitly. The downside of using a proof assistant, though, is kind of the same as the upside, which is that we have to dot our I's, cross our T's, and be very explicit about things. And that means this work can be very tedious. And what could be more tedious than reasoning about capture avoiding substitution? And here I'm just showing several examples of very different kinds of systems that you might care about. And in every kind of system, at some point, you have a need to consider an operation on syntax trees where you sort of iterate over the variables and you look for free occurrences of some variable and you replace all of them with some subterm. Now, this operation is very tedious. On paper, it seems fine, but in a computer, it's quite a lot of bookkeeping that you have to do. Sometimes you have two distinct variables that happen to share the same name. And during substitution, these variables might fall into the same scope. And now you have a conflict on your hands. So now you have to start renaming variables. And then you get this cascading renaming. And suddenly it's a lot to reason about. So for this talk, I don't want to think about renaming variables. Renaming variables doesn't quite fit into the vanilla DTM framework. So I'm going to pick some other representation of variables where I won't have to give sort of ad hoc names to things. And I'm going to pick Bruijn indices. There are other choices I could make. This is not really the point of the talk. I could use Bruijn levels or something called locally nameless, and the details would mostly be the same. If you've seen Bruijn indices, great. If you haven't, that's fine. I'm not entirely sure of my audience, I have to confess, but I'll tell you what's important about this. With Bruijn indices, every variable occurs somewhere in a syntax tree underneath a certain number of lambda abstractions. Let's just say we care about the lambda calculus. Other kinds of syntax work the same way. So you're underneath a certain number of lambda abstractions, and the innermost lambda, which is like the most recently introduced abstraction, is always considered 0. So at the top of the slide, you see a lambda term with named variables, and I've kind of color-coded the variables to help you read it a little bit. And at the bottom is the Bruijn representation. And I want to draw your attention to a couple things. If you look at the first occurrence of f, which is the leftmost one, that becomes a 0 with the Bruijn representation because it's referring to the first lambda in its scope, which is the one immediately to its left. But if you look at the second occurrence of f, that gets translated as a 1. And that's because where that 1 occurs, 0 is referring to the inner lambda, not the outer one. So we bump up 0 to 1, so we can kind of hop over the inner lambda and point back to the outer lambda. And then g is pointing at the inner lambda, so it becomes 0. What's the point? The point is that you cannot say that all occurrences of 0 are referring to the same variable. That's definitely not the case. Nor can you say that all references to what is fundamentally the same variable will have the same representation, because f could be 0 or 1. It depends where it occurs in the syntax tree. So put a bookmark in that idea because it's important. So if I were formalizing the lambda calculus in Coq, this is kind of the type I would write down for syntax. If I were using Tealeaves, this is exactly what I would write down. And the only thing that's interesting going on here is that term, this type term of lambda terms, is parameterized by this set var, which are var, or that's my variables. So these are the leaves of my syntax tree. So you'll probably recognize that term then is going to be some kind of endofunctor from sets to sets. And because I'm using Bruijn indices, all of my variables are natural numbers. So the type of my syntax is term nat. Nat is Coq's type of natural numbers. Okay, if I'm not using any kind of fancy category theory, the next thing I would do is write down an operation. It's called opening. It's the Bruijn equivalent of substitution. And I haven't written down all the details because they don't really matter. But what matters is that this operation has the same shape as the syntax itself because it's defined by structural recursion. And from a software engineering perspective, this is actually quite bad. And it's bad because it's brittle. When you define functions by structural recursion, they break all the time because they break if I change my syntax in any way. Say if I add a constructor, now my definition is wrong until I add a new case to my definition. This is actually a lot worse than it sounds because it's not just the definitions that will break. All of my proofs by structural induction will break as well. So I make one little change to my syntax because I'm messing around with some programming language I want to design. And suddenly I've broken thousands of lines of Coq code. And that's not great. I've done it over and over again, and I don't like it. So the problem is we do not want to have a tight link between our definitions and any one syntax like that of the lambda calculus. So we need some kind of abstraction here. Okay, basic insight. Syntax is usually some kind of monad. So let's look at that. It's not the best abstraction by itself, but let's figure out where it breaks. So here's the syntax again, and let's think about it as a functor. And there's two functors implicit here. One of them is my signature functor, sigma, right here. And here is where we start to depart from how I think other people have thought about this problem. And I'm taking a very first order view. I'm not explicitly thinking about things like variable binding. I want to think about the syntax as literally just a term algebra in the simplest way possible. So other than the variable case, which is treated separately, there are two constructors in the lambda calculus, one of which is binary, that's the function application. And the lambda, I'm just going to treat that as a unary constructor because it only takes a term as an argument, and that's the body of the lambda. And notice I'm not writing like lambda x.t because I'm not giving names to variables. So lambda is just lambda, and it's a unary operation. And then the syntax, which we originally called term, but now I'm switching to a more category theoretic way of looking at things. Then the set of terms is defined like this. And we say the set of terms t, given a set of variables v, is defined by this least fixed point expression. And you might happen to know that just by its very construction, T then is going to be the free monad generated by sigma. And when I say the free monad, I mean relative to a particular junction between functors and monads. But usually people just call this the free monad. And it's not the freeness of the monad that I care about necessarily, just the fact that it's a monad at all. So let's think about monads. We'll look at string diagrams in the category of endofunctors. Monads, of course, have two operations. There's the monad unit. And the monad unit, if I specialize the type parameter to v for variable, it's a function from variables to terms. And we're going to think about this as a coercion, or you could say inclusion of variables into terms. So this eta here is saying that every variable by itself is a very simple kind of term called an atomic term. Okay, fair enough. And the multiplication here says if I have a term of terms, I can flatten that into a term. So if I have a syntax tree and at the leaves of that syntax tree, I attach more syntax trees, then I can flatten the two layers together and I just get a syntax tree. So now let's switch to the Kleisli representation of monads. Again, I'm specializing to the type parameter being v for variable. So the argument bind here is a higher order function. It takes a function as an argument. And we're going to call that argument sigma a local substitution rule. And it's a function from variables to terms, but now it's encoding a choice of, given a certain variable, what term would I like to replace this variable with? Maybe I don't want to replace a variable, and then I'll just replace that variable with its own term. Every variable is itself a kind of term, so I can just return the variable itself. But in general, I can replace a variable with any term I like during substitution. And this is a local rule because it operates on the level of individual variables, which is a major theme of Tealeaves. If I want something that operates on the level of terms, then of course I feed this operation to bind. Now I have a function from terms to term, and it's going to visit all of the variables inside its input and apply sigma to all of the variables. So this seems like a general theory of substitution, but it's not the right kind. It's not going to work. And here's where things get interesting. Go back to our example of the lambda calculus. Remember, I'm using the Bruijn indices, so my type parameter is nat for natural numbers. And my so-called local substitution rules are functions from natural numbers to terms. But maybe you can see immediately, this isn't going to work. This is not the right thing at all. Why not? Because we said earlier, you can't look at a de Bruijn index by itself and figure out what variable it refers to. There's never a situation in which you would say, take every occurrence of 0 and replace it with some term t, because the different occurrences of 0 are not referring to the same thing, most likely. So if you want to operate on a de Bruijn index, you have to know how many lambdas is it under. You need some kind of context. Where is this de Bruijn index inside my syntax tree? So I will say that for my purposes, at least, monads on the category of sets suffer from two limitations. One is what I just explained. The notion of substitution you get is completely naive. You can look at an individual variable as like a leaf of the syntax tree, but you don't know anything about where that variable occurs. You don't know about its context, which for de Bruijn indices, the context is the number of lambdas that are underneath. The second deficiency is a little bit of a head scratcher. We haven't seen any indication so far of how we would define operations that are not substitutions. So a perfectly good thing to do would be to enumerate the free variables of a term, or to define a predicate that says this term does or does not have free variables. Bind is not going to work here. Bind gives me functions from terms to terms, not a function from terms to lists, for example. So things seem kind of bad, but we can fix this. And we're going to repair these two defects with two, I think, very simple ideas that are kind of orthogonal. And then we're going to merge these two ideas together. So if we want a notion of context-sensitive substitution, we're going to move to decorated monads. Maybe this has a standard term. If it does, I don't know of it, but it's a cute little idea. And then the second thing is when we want to reason about syntax as some kind of container, something I can like query for its elements, maybe enumerate them, we're going to look at traversable monads. As the name would suggest, traversable monads are related to traversable functors, which are very commonly used in functional programming. They were introduced maybe a decade ago and then gradually refined over a series of papers. And a traversable monad is just a traversable functor that's also a monad, but we have to impose a couple other conditions as well to make everything nice and coherent. And then we're just going to smash these two ideas together and we'll get decorated and traversable monads. And then this abstraction turns out to be the right thing, at least in my opinion. So let's look at decorated monads and we'll see what we get. So this is why I say this is syntax monads for the working formal metatheorist. I'm going to do the simplest thing possible, which is I'm going to go across my syntax tree and I'm going to look at every Bruijn index and I'm just going to pair it with the number of lambdas that it's underneath. I'm just going to annotate it with its context. Okay. Now, if we take a slightly bigger picture perspective, kind of zoom out, what I'm looking at this operation here, and by the way, there's nat for Bruijn index, that's the one on the right, and then there's natural number for the number of lambdas that I'm underneath. Both of these things happen to be natural numbers, but in general, they don't have to be the same to make sense. So if I zoom out, what I'm really looking at here is a natural transformation that has this shape. It's a transformation from T to T compose W times. And by this notation, W times, I mean the functor that takes a set A and gives you the set W Cartesian product A, where W is any monoid. For us, that's the natural numbers with addition, but it could be any monoid. So the question is, what are the axioms of this operation? How should I be able to reason about something like this? And the beauty of category theory is once you recognize the right kind of structure that you're looking at, the axioms will pop out. So in this case, what we have to recognize is that that product functor is always a comonad, regardless of what W is in the category of sets. And so the right thing to consider then would be the right, and I hear different terminology, co-modules, co-algebras, co-actions, I'm not sure what you want to call it, but the right actions of this comonad on a functor. And that leads us to the following two axioms, which I'm just going to present string diagrammatically. We get this axiom right here that says if I compute the context of every variable, and then I just delete that contextual information, that would be the same as doing nothing in the first place. Seems fair enough. The next law is if I compute the context of everything twice, that would be the same as computing the context once and then just making a copy of that context. So this idea is kind of nice, but the thing we have is not just a functor, it's a monad. So we're going to need to somehow relate the decorated functor to the monad structure. And the trick here is to recognize that that product functor is not just a comonoid of endofunctors, it's a bimonoid because W is a monoid. And I'll just go really quick here because I want to save time for questions and things like that. There's a basic fact about sets, which is every monoid in the category of sets can uniquely be extended to form a bimonoid, which is a monoid and comonoid on the same underlying object that are related in a nice way. So anyway, every monoid can be a bimonoid. And when I take the product functor with a bimonoid, that functor from sets to endofunctors, it's a strong monoidal functor, so it's going to preserve this very structure. Therefore, there's some general nonsense that says the co-modules of a bimonoid give you a strict monoidal category. This really is meant for the symmetric monoidal categories, which endofunctors are not, but the proof goes through anyway. And so we're going to say, if I have a monoid of, rather, if I have a monoidal category of decorated functors, then I can ask about the monoids in that category. And that leads me to the next two axioms. Oh, just a brief taste of what this category looks like. There's an obvious notion of a homomorphism between decorated functors. The identity functor is going to be decorated by just the monoid unit. I'll go quick because, of course, you can read the details in the paper. And if I want to decorate composition of two functors, I'll decorate them independently and add them together using that monoid structure from W. Now, right here, you might object and say, wait a minute, you're not allowed to cross wires in the category of endofunctors, not generally speaking. But in this case, that crossing of wires is the tensorial strength. Every functor on the category of sets has a, I think, unique tensorial strength. So I can cross wires right there, or at least I can cross those two wires. So now if I ask what is a monoid in this category, I will get the following two axioms. This one right here, and intuitively, this is saying that if I just look at a term X, there are no binders in scope. That seems correct. And then I get this axiom right here, and intuitively, it's saying that if I start at the root of a syntax tree and I go down, then I'm going to find more lambdas. I'm going to my context is going to accumulate as I go down the syntax tree. So that's decorated functors. There's an alternative characterization as well, which is kind of nice, but I'll skip it. Let's talk about traversable monads. The idea of traversable functors, not an innovation of mine, is that you want to be able to reason about a functor as some kind of container. I want to ask, like, what are its elements? And that's what traversable functors will give me. And just for some intuition here, if a first attempt that I tried for a while is to axiomatize the idea of being a finitary container, I could say let M be a monoid, and let's suppose that I have a function from Tm to M. And the idea is that if T is a finitary container, then I can take all of its elements. And if they're all elements of some monoid, then I can crush them together using the monoid operation. And this is a decent enough idea, but there's an even better idea, which is to generalize to lax monodal functors, which are also called applicative functors in this context. I'll go quickly. You'll have to forgive me for this. So then you get the idea of a traversable functor, and a traversable functor is one equipped with a distributive law from T compose M, where M is a lax monodal functor, to M compose T. And if M is the constant functor over a monoid, then this actually gives us that crush operation, but in general, it's much more expressive. So again, that's an old idea. That's been around. And as a string diagram, we can picture that as being able to cross an applicative wire over a T. I'm drawing my applicative wire in yellow. Okay, but we have a traversable monad. How do we deal with that? Well, fortunately, traversable functors also form a nice monoidal category. There's an obvious notion of a homomorphism between traversable functors. It just means a natural transformation. We can sort of scoot past that crossing of wires. And you get an obvious notion of identity and composition as well. So I can ask, what is a monoid in the category of traversable functors? And the force of that is that my monad operations will also have to just be able to scoot past that crossing of wires. So I'm led to the following two axioms. One says I can scoot the unit past the crossing of wires. And if you think about what this says for syntax, it's saying, suppose I have an atomic term, which is just the variable y. What variables are in that term? And the answer is y. Seems like a reasonable axiom. You also get this axiom right here, that the join has to be able to scoot past that crossing of wires. And this too has a very intuitive characterization that says I can treat my functor as like a container. I can query about its elements. And if I sort of flatten two layers of syntax together, that acts in a very coherent way with querying for elements. So now we have decorated functors, we have traversable functors, and we just combine them. I define a decorated traversable functor as one that's decorated and traversable and also satisfies this little coherence law right here that says in a precise sense, both of these structures are homomorphisms with respect to the other one. And these two give me a monoidal category. So you can guess what I'm going to do. I'm going to define a decorated traversable monad as a monoid in this category. And very explicitly, that means a DTM is a monad, and it's a decorated functor, and it's a traversable functor, and it's subject to every single law I've presented so far. So just take everything I've said and add it all together. That's a DTM. Okay. Let's talk about the application of this real quick, and then maybe we'll have time for like one question. DTMs have a Kleisli style presentation, which I've shown here. I've tried to color code it in a way that corresponds to the rest of the drawings. But we have the single combinator bind DT. This is like the bind operation of a decorated traversable monad. And when you present DTMs this way, you just get a set of 4 axioms that are totally equivalent, and we verified this theorem in Coq. It's not surprising, but it is extremely tedious to prove. Here is what my Kleisli morphisms look like. And intuitively, what's happening here is f is some operation on syntax that it's an operation on syntax. And what's going on in this diagram is I first ask, what is the context of every single variable? That's the red wire coming out. And then I apply f to every variable, which is the black wire, and its context, the red wire. And then f is going to spit out some term, which is the blue wire. And also it can be wrapped in an applicative functor, which is the yellow wire. And so bind DTF has this shape. And there are some nice string diagrams in the paper where you can kind of see this in action. And here are the axioms of DTMs when presented this way. It's got some notation I haven't introduced. But the point is these axioms are very simple and they're pretty easy to prove automatically given a specification of a syntax. So what do we actually do with this idea? And this will be probably my second to last slide. Like I said, we have a calc library called Tealeaves where we formalize this idea of DTMs and the two different presentations and their equivalents. And we have used DTMs to reason about capture avoiding substitution using something called locally nameless, which is kind of like the Bruijn indices. And we were able to completely reproduce the functionality of a tool called lengine, which previously was like the state of the art for locally nameless syntax. lengine is a code generator. It is an extremely complicated tool. Basically, you tell it about your syntax. It generates a bunch of text files that contain calc code that contain proof scripts. Those proof scripts use a bunch of totally incomplete heuristics to try and prove things about your syntax. Whereas our tool, it's just a calc library. You just download it from GitHub, compile it. It's totally static, it's completely verified, and it's based on a principled theory, but it does exactly the same thing. So it's kind of nice. And we suspect that others will find this DTM abstraction useful, although for the most part, we've mostly used it to think about syntax. So in conclusion, we presented, what else is in the paper? Just more string diagrams, basically. I'll show you, the paper explains more in detail about why these two presentations are equivalent. In conclusion, we've presented some very simple, but seemingly kind of novel concepts, this idea of a decorated traversable functor and a DTM. We've shown two ways of defining DTMs that are totally equivalent. And we argue that DTMs are the right abstraction for reasoning about syntax, at least in the fashion that we have always reasoned about syntax. And I will conclude right here.
Thank you, Lawrence. Thank you. Let's thank Lawrence.